So, as you know, the conceit of this series is that I have 24 hours to study for my qual. Except that was like, what, 6 weeks ago? What is the chronology even? So what we could do is try to hit the broad strokes, understand the big picture, and do our best in the qual tomorrow. That's really all anyone can ask of you. Or we could ignore all that. Behold, the answer to our prayers. We've talked before about different ways to build a topology if you already have one, like with a subspace. We're going to do a similar thing today with the product topology. Remember that the product of two sets, A and B, is just a new set, A cross B, where the elements are ordered pairs little a, comma little b, and we visualize this as a plane with AB axes. So the question we're going to ask ourselves today is, if we start with two topological spaces, x and y, what's the natural topology to put on x cross y? Well, here's a totally natural thing to do. We'll put a basis on x cross y, which consists of subsets u cross v, where u is open in x and v is open in y. That seems like a normal thing to do. Feel free to go and check for yourself that this does indeed form a basis. In fact, if you want to, it's equivalent to just let u and v be basis elements of x and y, and the whole thing follows through. That is, assuming that you have bases for the topologies on x and y. We'll call this basis we've defined on x cross y the basis of rectangles. Well, but hang on, why should it be called the basis of rectangles? Consider the example of r cross r, which we'll just write as r2. I said before that you can visualize a set product as a plane, and this is literally the plane that we're used to thinking of. So what's the product topology on r2? Well, remember that a basis element of r, side note, pretty much from here on out, if we don't specify a specific topology on r, we mean the standard topology. A basis element of r is just an open interval. Let's draw an a comma b in the first r and a c comma d in the second r. Then the basis element is a comma b cross c comma d, which is a rectangle, hence the name. The basis of rectangles is a totally reasonable topology to put on x cross y, and so we say that the topology generated by the basis of rectangles is the product topology on x cross y. Well, cool. Is this a time machine? Okay, there's no way I'm getting mixed up in any time travel shenanigans. So that's the product topology. Except, hang on a bit. The product of two things is all well and good, and we can imagine how to take the product of three spaces. It should be given by a basis of cubes, where a basis element consists of products of open sets from one of each of the three factors. And so of course from here we can bootstrap up to a product of 4 spaces, or 5, or 10, or 200, or Google Mini. Any finite amount of topological spaces, we know how to define their product. But those are just finite products. We don't want to be tethered to the realm of finite products. We want to take products of infinitely many things. Uncountably many, if we're feeling particularly risque. What does that set product even look like? Forget about putting a topology on it. What is the set product of infinitely many or uncountably many sets? Here's the idea. We can think of an ordered pair a comma b as a function f from the set 1, 2 to the set a cross b, where f of 1 equals little a and f of 2 equals little b. This is just a fancy way of saying that an ordered pair is a choice of a point in A to be your first coordinate and a point in B to be your second coordinate. So with this idea, we can pick out a point in the set A cross B, and then the set itself is the collection of all such possible choice functions f from 1, 2 to A cross B. Or, in other words, all possible choices of first and second coordinate. And now, this is pod racing. We might not be able to generalize A1 cross A2 cross A3 cross etc, etc, etc for infinitely many, or even, especially, uncountably infinitely many sets. But we can generalize choice functions. In fact, it's no concern at all to have a function with an uncountable domain. You think about them all the time. So let J be an indexing set, which I want you to think of as like 1, 2 from before, or n if you want to index over countably infinitely many things, or an even larger set if you need it. A choice function, which we'll also call a J tuple, is just a function from J to X. We can think of it literally as a function where you evaluate at some alpha in J and get a point in X, or we can think of it as a tuple, where we use this notation. For some arbitrary alpha in J, the alphath coordinate of the tuple is X sub alpha, but that's just the evaluation of the choice function at alpha. So from our toy example from before, f of 1 equals a and f of 2 equals b is the choice function, and a comma b is the tuple. And the set a cross b is the collection of all possible choice functions slash tuples. So now, to define the set product in this general sense, let's say we have a whole host of sets, one for every alpha in our indexing set J. We'll write a sub alpha for the alphath set. The product of the a sub alphas, which we'll write like this, is just the collection of all possible choice functions from J to the union of the a sub alphas, where the alphath coordinate lives in a sub alpha. Okay, this is all well and good, but we want to build a topology on these sets. So say I have a whole bunch of topological spaces X sub alpha. What's the right and proper and natural and God-fearing topology to put on their product? You might think that we could keep building boxy, rectangle-ish bases, which is to say, a basis element of the product topology is just a product of U sub alphas, where each U sub alpha is open in the corresponding X sub alpha. You'd think that, but... Okay, to be fair, this is what we do in the finite case. But the reason this stinks in the infinite case is because it can cause some hot garbo to happen. For instance, let's let n be our indexing set, and consider the topological space that is that many copies of R. We write R2 for R cross R, 2 copies of R. We write R3 for 3 copies, and so we'll write Rn for n copies of R. And let's give Rn this boxy basis. And now that we've done this, consider the function f from R to this Rn, which is defined to be, for any t, the tuple t, 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 on and on and on. Countably infinite copies of t. God, we hope f is continuous, right? I mean, come on, it has to be, right? And yet, the set -1, 1, cross -1/2, 1/2, cross -1/3, 1/3, cross -1/4, 1/4, I think you get the idea, is a product of basis elements. So it's a basis element in Rn, and therefore it's open because it's a basis element. And yet, the preimage of this set is 0, which isn't open in R. F ain't continuous, folks. So this box topology is the wrong idea. Here's the right idea. Build a basis on the product of X sub alphas by taking the product of U sub alphas, where U sub alpha is open in the corresponding X sub alpha, except for all but finitely many alpha, U sub alpha is the whole space X sub alpha. First off, notice that this will agree with the definition in the finite case, since the for all but finitely many condition is gonna be true. There's only finitely many alpha in the first place. Second, in the infinite case, you do get something genuinely different than that horrible example from before. Here's a real quick example to see why the box topology and the product topology give you different spaces. Start with countably many copies of the set 0, 1, each with the discrete topology. Elements of this product set are infinity tuples, x1, x2, x3, and so on, where each coordinate is either 0 or 1. If you put the box topology on this set, you'll just get the discrete topology. To see this, you just have to show that any arbitrary infinity tuple is an open set, which isn't hard to do. Then, if all the singletons are open, every set is open, and you get the discrete topology. But if you put the product topology on this set, then you won't get the discrete topology. And all you have to do to see this is cook up a single set which isn't open or closed. Because in the discrete topology, every set is open and closed. Here's a candidate. The set 1, 0, 0, 0, 0, and 0, 1, 0, 0, 0, 0, and 0, 0, 1, 0, 0, 0, 0, and so on, is not closed. It's not closed because the element 0, 0, 0, 0, 0 is a limit point of this set. and it's a limit point which isn't included in the set itself. What an excellent exercise to make sure that you're on top of your game as far as limit points are concerned, way back from episode 4. Homework time. Have at it. Also, just to quell our deepest insecurities, it's a theorem that if you give the product of x sub alphas the product topology, not the box topology, then a function f from a to the product of x sub alphas is continuous if and only if the functions f sub alpha from a to a single x sub alpha are continuous for all the alphas. This is exactly enough to guarantee that we won't run into any yucky business like the function t mapping to t being discontinuous from before. All our deepest insecurities have to do with the existence of pathological topological spaces, right? It's not just me. Yeah, that's right. This is just a letter reminding me of my quals first thing in the morning. Man, I really wish I had more time to study. Behold, the answer to our prayers. And we can imagine how to take the product of 3 spaces. It should be given by a basis of cubes, where a basis element is just With this time, we can actually dive a little bit deeper into the product topology. Why is it that the product topology has such a seemingly artificial construction in the infinite case? We've seen a concrete example for why the box topology is bad and the product topology is good. But why is it that this specific construction, that all but finitely many of the u sub alphas are x sub alpha, the one that makes everything work? The real stars of the show in the product topology, whether you have finitely many or infinitely many factors, are projection maps. A projection map is just a map onto one of the factors of the product, which, when you plug in a point, tells you the value of your point at that specific coordinate. That's a mouthful, so here's an example. On the set x cross y, there are 2 projection maps. The first is a map x cross y to x, defined by sending an ordered pair x comma y to x. And the second is a map x cross y to y, defined by sending x comma y to y. We call projection maps pi for p for projection. So we just defined pi 1 and pi 2 on the product x cross y. And of course, this completely generalizes. If I have a product of x sub alphas, then I can talk about the beta-th projection for some beta in our indexing set J, and it's just the map from the product to x sub beta, defined by plucking out the beta-th coordinate. Well, these projection maps are alright. I guess I'm a little bit on edge as far as intuition is concerned. One thing we ought to see is that projection maps are continuous, right? And in fact, they are. What a magical, happy world we live in. They are very clearly continuous functions. If J is any indexing set, then the product of x sub alphas has J many projection maps. Pick a random one, the beta-th one, from the product to x sub beta. Let's show that the preimage of an open set is open. So let u sub beta be open in x sub beta. The preimage of u sub beta is u sub beta cross all of the other factors x sub alpha. And that's a product of open sets, all but finitely many of which are the whole space. In fact, all but one of which are the whole space. Thus, that's an open set. It's a basis element, and the projection maps are continuous. And not only are the projection maps continuous, but the product topology is the coarsest topology that you can put on a product of sets that makes the projection maps continuous. We haven't yet talked about coarseness, or its complement fineness, but it's easy to describe really quick. The idea is that if we take a set X, then there can be different topologies that you put on X. Sometimes it happens that if you hand me 2 topologies, tau 1 and tau 2, then it could be the case that every open set in tau 1 is also in tau 2. When this happens, we say that tau 1 is coarser than tau 2, or that tau 2 is finer than tau 1. The image I have in mind when this happens is gravel. I'll explain. If you have a coarser topology, then you have bigger chunks of gravel. You have bigger, clumsier open sets. If you have a finer topology though, well, you still have all the big open sets, but you have potentially smaller open sets too. And so you can talk about nearness a little bit more delicately. So a more big picture way to think about the product topology is that it's a topology that makes all the projection maps continuous, and it's the coarsest topology that does the job. And in fact, you can generate the product topology by just requiring that preimages of open sets under the projection maps are open. And if we have any other topology that makes the projection maps continuous, then the map from that topology to the product topology, which is just the identity on sets, is continuous. It necessarily has to be so. That's just a slick way of saying that the product topology is coarsest. It's the smallest or weakest or first or initial topology that you can put on the product of sets that does the job. Oh, and just for fun, what's the finest topology that makes the projection maps continuous? Here's a hint. In this topology, every map out of it will be continuous, not just the projection maps. I'm supposed to be by at any minute and pick up this letter, but it's not there. Okay, I'm basically back to when I was just before I used the time machine. But there's still more studying to do. This is just a letter reminding me of that. The time machine is just over there. One more use can't hurt. And we can imagine how to take the product of three spaces. It should be given by a basis of cubes, where a basis element is just With this extra time, we can actually dive a little bit deeper into the product. Down here this time. Okay, so maybe now we have a better idea of why the product topology is what it is. It's determined by the projection maps. Except, hang on, why should we define a topology in terms of maps? Like, why is that the sensible thing to do? It feels like we're just kicking the can as far as motivation is concerned. The truth is, there's larger forces at play here. A perspective that it's not really the objects that we care about, but instead the objects and the right maps between them. Or really, just the maps. So now's as good a time as any to get our first taste of category theory. Now, we're not going to go anywhere in depth in category theory today. There will be plenty of time for that in the future. All we're going to do today is give you just enough to give you a first impression and convince you that there's a rich theory bubbling under the surface here. Okay, so all a category is a collection of objects and arrows that behave the way functions between sets do. That's okay for now, that'll do. The specific category we care about is going to be top, where the objects are topological spaces, and the arrows are continuous maps. In this category, the product topology is a specific instance of a more general construction of a categorical product. So let's give that general definition. To keep things simple, we'll just take the product of two things. The categorical product of two objects x and y is a third object p with maps pi1 from p to x and pi2 from p to y, such that if we have any object z that has maps f1 from z to x and f2 from z to y, then there's a unique map from z to p that makes the following diagram commute. All it means for a diagram to commute is that if there's multiple ways to go from one point to another, then it doesn't matter how you compose the arrows, you'll get the same result. A concrete, that's a pun, but you don't get it yet. A concrete example is that in our diagram, f1 equals pi1 composed with f, since those are two different ways to go from z to x, and thus we say that triangle commutes. It's not too hard to see that this categorical product produces the actual set product and the coarsest topology on that set, such that the projection maps pi1 and pi2 are arrows, or in this category, continuous maps. And in fact, any finer topological space z gets a unique map from Z to P. I understand that I kind of just hit you over the head with category theory out of nowhere here, but here's 2 words of reassurance. The first is that we're going to discuss category theory more in depth in the future, so it's okay if not everything clicked right now. And the second is that this is actually a really good way to learn category theory. At first, it's weird and wacky and abstract nonsense, but it starts to feel more and more natural the more examples you have in your tool belt. So, to top it off for today, here's a little exercise. Can you describe what the categorical product of 3 objects needs to be? Also, do you know of any more categories? And in those categories, can you construct product objects if they exist? I mean, they don't always have to. For instance, maybe you know about groups and group homomorphisms, so you could try to construct the categorical product of 2 groups. And in fact, if you know the explicit non-categorical construction for the product of 2 groups, then it should feel very similar to the explicit non-categorical construction for the product of 2 topological spaces. So that really tells you there's something deep going on here. Or for another example, you could build the set product categorically. It's good practice. Well, I'm all set, Chunk. Now that I have this time machine, I have all the time in the world to study. Hang on a second, you're right. If I took this time machine from my first past self, then my first past self can't travel back in time and become my second past self. And if my second past self doesn't exist, then he can't travel back in time and become me. But that's not good. I want to be Chunk. Look, there he goes. He took the time machine before my first past self could use it. Now my first past self won't go back in time, and he won't become my second past self, and he won't become me. But Chunk, my studying. You're right. It's the only way. I guess the qual really is going to be tomorrow after all. Oh well, back to studying.